Hello. This lecture is about how to solve for circuits that are called series circuits. In other words, how to determine how to calculate voltage, current, resistance, and how to use those later in figuring out aspects about combined circuits. Series circuits are the most simple type of circuit. They have only one path for electricity to flow. And Ohm's law, which is I equals voltage divided by resistance, and the power formula P equals voltage times current, apply to any part of this circuit or the whole circuit. That's actually kind of important. So these formulas are pretty straightforward. They're not hard to use, but the thing is you got to remember that they can be used in any part of a circuit or a whole circuit, as long as you're thinking about your logic correct with how we solve for series circuits, and later on how we solve for parallel circuits, and finally how we solve for combined circuits, which have aspects of both series and parallel circuits. So in this case, once again, one path for electricity to flow. We're going to find the total resistance of the circuit by simply adding up the resistance values. We're also going to find that current is the same everywhere in the series circuit. And finally, we're going to discover the voltage or potential difference that's used, and I want to use that in air quotes, and I'll talk about that in a few minutes, across the resistors adds up to the total voltage provided by the battery or the power source in the circuit. So those rules are going to apply for any series circuit. So I'm going to do an example here that I think I'm going to provide to you on a written document as well. So in this particular case, and I should look to see what it looks like. I've got a power source up here. It's a 12-volt power source. If you remember, the short line is the negative, the long line is the positive. We will think of positives as flowing, so they're going to flow away from the positive because positives repel positives. I'm going to have an ammeter, which I locate anywhere in here. I'm going to use that as a red color. And I'm going to call that, again, an ammeter. We put ammeters in series with the part of the circuit we want to measure current because the current's going to be flowing through the ammeter. That's going to allow us to measure it properly. Next, we're going to have a resistor here below this. One at the bottom of the circuit. And one over on the left side of the circuit. I'm going to say that this resistor, which is the first one, is going to have 5 ohms of resistance. And remember, that little weird horseshoe thing is the symbol for ohms. Down here, I'm going to have one with 3 ohms of resistance. And over here, I'm going to have one with 4 ohms of resistance. So the other things I'm probably going to want to solve for are to figure out the voltage across each of these. So I'm going to put a voltmeter here. Now, a voltmeter has to be hooked up in parallel, meaning beside the device you want to measure the voltage of. Why? Because it literally is measuring a difference in potential energy from one side to another. So really, this is joules per coulomb of energy that's different from here to here. If I put a voltmeter across a wire, say down here, if there's no resistance, it's not going to take any effort or energy to go through that wire. So this voltmeter would read 0 volts. But here, it does take effort or electrical energy to push the electrons through in this location. So we need to measure a difference from one side of this resistor to the other. Likewise, we're going to have a voltmeter here and a voltmeter here. So the first thing that I'm going to want to do, almost always when solving for circuits, if I don't need to simplify the diagram, I'm going to want to make sure I find the total resistance. Well, the total resistance I just find by adding up the resistors. You might say, well, why is that? In this case, that's 5 ohms plus 3 ohms plus 4 ohms. 5 plus 3 is 8. 8 plus 4 is 12. 12 ohms. I've got a little demonstration to show that, so give me a moment to get this material because I forgot it. Okay, so this is a hose used to carry air or water. And I think the idea behind this is if you have it connected to something like air here, that's fun. The same amount of air is going everywhere in this hose because there's only one hose. But if I put a crimp in it, I can slow the amount of air passing through that hose. It doesn't slow it just at the crimp, it slows it everywhere in the hose. It slows the amount coming in, going through here, through the crimp, and after the crimp coming out. So if I have multiple kinks in the same hose, you could imagine that it's going to affect the whole hose even more. So if I have 2 crimps, it's going to slow down the flow of air more. 3 crimps, even more. So if I have a crimp that's loose, it'll only slow down the flow of air a little bit. If I have it where it's tight, it's going to slow it down a lot. Now this liquid or flow analogy is not perfect with respect to electricity, but it's not bad. So we'll use that to start our understanding. And I've got water over the floor, which is going to be fun. All right, so in this particular case, I've got 12 ohms of resistance. The next thing I would probably want to do is figure out the total current. So that's the current going through here. Now notice, it's not going to matter whether I put the ammeter here, or here, or here, or here. If I have only one path for the electricity to flow, the current's got to be the same everywhere. I can't have more electrons or charges passing through this spot than this spot or this spot. And that goes back to the law of conservation of matter. So in this particular case, you remember the symbol for current is I, so I'm going to say the total current is going to equal to total voltage divided by total resistance, which I've already written the number down. That's not helpful. So that's 12 volts over 12 ohms. That's 1 amp. So the current in this circuit is 1 amp. What about the voltages? Well, basically, if I have a 12 voltage difference from this side of the battery to this side of the battery, that means I've got to use up 12 volts total throughout this entire path. Hopefully it makes sense that a circuit element with more resistance is going to take more voltage to overcome than a circuit element with less resistance. So it's going to take more of this voltage, which I like to think of as like the push that makes electricity go. And resistance is the opposition that opposes that. So I'm going to use a different amount of voltage here than here than here. How would I figure out how much? Well, I'm going to go back to Ohm's law, but I'm going to rearrange it. And I'm going to say V is equal to I times R. Now I know that the current going through each of these resistors is the same. It has to be because it's a series circuit. So in this case, if I want to figure out the voltage across the 5 ohm resistor, I'm going to say 1 amp times 5 ohms. And that's 5 volts. Same way, the voltage across the 3 ohm resistor, 1 amp, 3 ohms, 3 volts. And then finally, the voltage across the 4 ohm resistor is obviously going to be 4 volts. Now notice my wording here. I'm saying that it's a voltage across the resistor. It doesn't go through it. Voltage doesn't flow. It's current that flows. So the current is flowing through the resistor. Voltage is a difference in potential energy from one side to another. The other thing that's nice by doing these calculations, what we can see is that I lose 5 volts across the first resistor, 3 across the next one, 4 across the last one. 5 plus 3 plus 4 means I've used up 12 volts. that agrees with the fact that I have a 12 volts difference from this side of the circuit to this side of the circuit. So I should use up all the voltage that's provided. Now, the reason I set up this circuit like this with the 5 ohm resistor first is a lot of times people always think that you have the most voltage or the least voltage used across the first resistor. But if I switch this, and I made this the 5 ohm resistor, and this the 3 ohm resistor, the values don't change. It's just that this one would end up being the one that uses the most voltage. In this particular case, if we want to figure out the power in the circuit, by the way, power is equal to voltage times current. So the total voltage here is 12 volts. The total current is 1 amp. So this would be a 12 watt circuit. That would be the amount of power that's provided. So hopefully that makes sense, and you can ask me questions about those during office hours.